So if everybody can hear me okay, I think I'll just go ahead and get started. I don't think I need to listen to anybody since it's just me talking to myself. Sound good? Okay, perfect. All right, so I'm really, I think I'm gonna give a less technical talk than what you've heard today. At least what you heard the last two talks were brilliant. And I'm gonna end on a little bit of a lighter note. So I was asked to give like a, I was asked to give a sort of overview of the Python ecosystem for neuroimaging, and which I'm really happy to report is just in a fantastic condition, honestly. I think we've come a long way from where we were. I've been involved with the neuroscience community, you know, I don't know, 10 years now. I started out doing stuff in FSL with Bash and fighting with my advisor, trying to get permission to use R and then permission to use Python. And, you know, to be honest with you, it was a little bit harder to justify at some point in time because the tools were not there yet. And there was times that it took a lot more effort for me to do what I wanted. And now I think it's a lot easier to justify because I think you're going to be doing better science. So hopefully I just give a slight overview of other projects that are going on, how they interact with nilearn. And really I want to give more of like a high level overview of what are good principles. So yeah, I'll go to my overview slide. What are good virtues of a modular ecosystem? So what does it mean to have an ecosystem in the first place? So I'll give you a really quick tour. And then I'm going to use Neuroscout as a case study, of course, because it's my project. And hopefully, you know, it's not really supposed to be about Neuroscout. It's hopefully just shows you how there's different pieces that come together to make Neuroscout possible. And it's really thanks to those projects that Neuroscout even exists. And what are some lessons that we can gain to maintain this healthy ecosystem and to make it even stronger? So, you know, first of all, I think that we want tools that will match our scientific aspirations. So we honestly have extremely lofty scientific goals. We want to image and visualize the human brain, the structure and the function, and we want to relate it to cognition, behaviors, and traits. We want to understand how the brain gives rise to complex mental states, create biomarkers of brain disease. I mean, these are things that could change the world if we do them right. But unfortunately, there's obviously been a lot of crisis about whether or not we're doing that. And I think one of the key factors to doing science that really matters and changes things is trust and transparency. So do we even trust our results? Can we understand, related to software, can we understand the code that produced these results, these images? And can we fix bugs if any arise? Or is it going to be pretty much completely impossible? And can we share these results and these pipelines and the data, and can our colleagues reproduce and modify our pipelines and reproduce our results? So these are key scientific principles that I think we want our software to help us with. You know, in neuroimaging, there's a really wide range of analyses, and I think they're fairly specialized. So there's like image pre-processing, there's manipulation of images. We have all sorts of structural analysis, different types of functional analysis, decoding, mass univariate GLM, functional connectivity. We need visualization tools and maybe even meta-analysis tools. So does this ecosystem support this wide range of scientific questions? And so, I mean, one place to start is, you know, what is wrong with monolithic packages? So, you know, SPM, AFNI, FSL, they're really robust and mature neuroimaging workflows and software. And honestly, I think that to some extent, these can be very appealing to beginners because they're potentially easier to use and understand. So why don't we use these monolithic packages? Why are we trying to, you know, support a different system? And I think even though I have to say FSL is not actually purely, you know, fully monolithic, it's actually, you know, modular, thankfully. In practice, most users are going to use these packages in a monolithic way. They're not going to often naturally mix them with other pipelines. And I think really more importantly, because the code base is often in a language, at minimum, a language that you may not be scripting with. So it's written in a language that you're not actually putting together your scripts in. And just of the way that the code is organized, it's more opaque. And so this requires more expertise to debug. So if there was ever an issue that came up that was actually affecting your results, I think that might be really hard for an end user to do. So this kind of encourages a really large gap between an end user and a sort of software maintainer, software developer. And I think that's generally a bad thing. It's amazing that we've actually been able to get this far doing that, because it does require an extreme amount of time from the software maintainers. But I think we want software that will encourage introspection and hopefully have a more diverse and sort of distributed maintenance, regime, if you will. So what we really want, I think, is modular design. So like I said, I think specialized analysis pipelines sort of naturally tend to monolithic structure. Modular design is really hard to do properly, but it has some major advantages. So first of all, I think code is easier to test. So when you have a piece that has a small defined function, it's easier to say what it should do. So when you have a library that is only doing I/O, it's easier to say these are the results that you get from this I/O library. So you can increase the testing, have greater coverage, and in turn increase trust, which again is scientifically important. Then this also makes your code more reusable, right? Because it's not just something that I'm going to use in my package. So if FSL, for example, well, I don't know if FSL is a best example because it's actually somewhat modular, but if a package has a tool that's really useful, but it's deeply embedded into their monolithic framework, it's going to be hard to reuse in another context. Somebody else is going to write something that maybe is a port of it that is exactly the same. So now you have two codes in two different languages with greater maintenance cost. And I think if you do things in a certain way, it can also promote extensibility. So you don't just want your code to be used in the way that it was intended to, but hopefully it can be expanded and built upon to build more complex pipelines. So what are some principles of a healthy ecosystem? I think we want modular, well-defined, reliable building blocks. So we want to build upon these really core blocks. These blocks should have clear, consistent APIs. They should be easy to understand. They should be predictable. They should hopefully behave similarly in different scenarios. They should be accessible. The code hopefully is somewhat easy to understand, and that's a Pythonic principle. Obviously, great documentation we've heard about that really helps with onboarding for new projects. I think ease of contribution is really important. So if there's developer guides, if there's active, receptive community that can help, and really in relating to modular design, interoperability. So modular design and standard formats really are what's going to make it easier for tools to interact and actually be an ecosystem instead of a bunch of silos. So with that said, let's take a quick look at the neuroscience, neuroimaging ecosystem. So first of all, this is really all possible because SciPy, and I think Python in general, has a very modular ecosystem type of approach. So there are specialized libraries that are extremely good at doing one thing. So NumPy is just, we can all use NumPy. We can all accept NumPy objects, and we can all trust NumPy to do its job. So I don't necessarily have to worry about how to map data to memory. Somebody else has done that. They've done it really, really well, and I can take that piece and I can trust it. So we have this amazing set of tools from Python that we can build on. And then we have a set of tools that I think help us with some of the basics, like, for example, nibabel critically helps us with reading neuroimaging file formats. We have tools we have data standards like BIDS and tools like PyBids to help us deal with those data standards, or tools like Hudicom to convert to those data standards. And then we have tools that can help us also get data. So obviously without data, can't do much. And then the ecosystem has really grown to have very mature packages for data analysis. And so PyMVPA, nilearn, I put nilearn.stats separately because that's a new addition to nilearn. And NiPype, MNE, these are all very mature, and I think for the most part designed in a modular way. So there's a lot of pieces of these different libraries that as a developer, I can pick and choose and use different pieces without necessarily having to buy into everything about that package. So I think that's a really good design principle. NiPype is, I think, a really interesting example because if you're not familiar with NiPype, I'll talk about it a little bit more, but NiPype is essentially it's a workflow engine for neuroimaging workflows. So one of the main things that allows you to do is use existing tools that are not necessarily in Python and use them in a Pythonic way, essentially, have a clear, consistent API. And then, of course, we have also tools for plotting, which are really important in neuroimaging because we're trying to visualize the brain. And so on top of these sort of core packages, then we have a huge variety of sort of applications, if you will. So this is just a small subset. So, I mean, I'm sure there's a lot of people watching. They're like, hey, where's my package? There's too many, but this is just a random selection I could find. And as you can see, this is actually almost overwhelming at this point. But I think it's a really good sign that we have a really mature ecosystem. So obviously I can't talk about all these packages. So I'm just going to use Neuroscout as an example, and I'm going to touch on some of the tools that Neuroscout relies on and how they work together. So what is Neuroscout? This is the project that I've been working on. Neuroscout is a web-based platform for fast and flexible reanalysis of naturalistic fMRI. So we have taken a bunch of open movie fMRI data sets and used machine learning to annotate them. So we have potentially hundreds of possible regressors on, a dozen open naturalistic data sets that, look at different movies like Raiders, Forrest Gump, etc. So a really diverse set of data and a huge set of regressors automatically generated. And then we've created a web platform, which you can go to if you want, neuroscout.org. And users can create custom statistical models using a web-based platform. So the idea is really to have automated data retrieval, modeling, and sharing. So you can go from the web-based platform to create a model. It creates a package that's a self-contained bundle with everything you need to run that. And in one line, you can run that bundle, get fitted results, and upload them to NeuroVault. So, this is only possible because of this ecosystem that exists. So almost everything that Neuroscout is, not entirely everything, but almost everything that Neuroscout does is just to glue these different pieces together. And so actually, as a maintainer of Neuroscout, most of my time, maybe not most of my time, but a large percentage of my time is spent maintaining the upstream packages that we rely on. So first things first, it's not really exclusive to Python, of course, but I think this is a great example of one way to increase interoperability is data standards or just standards in general. So if you're not familiar with BITS, which I'm sure most of you are, it is a standardized file folder structure for neuroimaging datasets. Using a combination of nifty headers and JSON sidecars, we can keep track of the metadata of different files, and using a structured file format, we can also keep track of different attributes such as the subject ID, task, etc. And so what's great about this is this allows for generalized automated analysis as all the information is programmatically accessible. So this is awesome, and this makes my job, not just easier, it makes it actually possible. So that's just the foundation. I think that's one way to allow interoperability between the different parts of the ecosystem. So now that we have a data format, we need to retrieve our data. So I could talk about DataLad all day long, but I'm not going to because there's a great handbook. So DataLad is a Python data management tool based on Git. So in short, it helps you keep track of your code, data, and metadata in Git repos, that's supposed to say. It's a tool for discovering, consuming, and publishing large remote data sets. So essentially what we've done is we've taken data sets and we published these pre-processed data sets. And so this is actually just a short snippet from what Neuroscout is doing to get the data. It's simply just saying, install this data set and get, for example, here, I can, in a granular way, say, just get all the files related to subject one. That way I don't have to download the whole data set. If I'm only running a model that, oh, it's hiding behind my head. Okay, well, that's not good. It's going to hide a bunch of stuff behind my head. But essentially, the idea is you can, in a granular way, control the data that you're getting. So I think this is really cool. I definitely encourage you to check it out. And here's an alternative. So nilearn has a datasets module, which I'm sure you're familiar with, but I think this is another great example. I think we need this sort of stuff. We need built-in dataset fetching. This is really important for reproducibility. This is really important for examples, documentation. So here's a short code snippet of how you could do something similar using nilearn. So, one thing that's a running theme, I think, in this talk I want to make is ecosystem doesn't necessarily mean that everything has to be done the same way. So there can be parallel solutions. That's okay. There's going to be times that we're going to want to merge approaches, but I think it's not necessarily true all the time. So we have a way to get the data. Now we need pre-processed data. So this is where fMRI prep comes in. So fMRI prep is a robust, reproducible pipeline for minimal pre-processing of fMRI data. And it's built using NiPype. So like I said, NiPype is a platform for providing a uniform Python API to heterogeneous existing neuroimaging software. So that's really the key, I think, contribution of NiPype. It's a way to essentially access different interfaces that are not written in Python, but we know provide very useful neuroimaging tools and provide a way to access them from within Python in a way that makes it easier to mix different elements of them and create a more complex workflow. And I think this is actually a really interesting example because in some ways, I just told you we're trying to get away from using these other tools, but it goes to show that really the only thing that these tools are lacking, because they're fantastic tools with great algorithms, it's really just this uniformity and this way to make them interoperable. So NiPype solves that problem. Although I will say one con of NiPype, if you're using it in the intended way, is that if you're using an FSL interface or an SPM interface, there's still a greater distance between you, a Python developer, and the code. So you might still run into the same problem that, if a bug is going on FSL and using NiPype to access FSL, you might have a nice uniform API for it, but you're still going to have the problem that it's going to be hard to contribute upstream to FSL. So it's something to keep in mind. So this produces a nice data set. It's actually something that then we use Data Lab to create this remote repo that we then download. And so once I've done that, really, I'm actually it's not even Neuroscout anymore. So now it's actually Fitlins. So this is, you've heard from Chris earlier today, and Chris is the main maintainer of Fitlins. Fitlins is a BIDS-aware GLM estimation framework. So Fitlins takes a BIDS data set, which you know what that is, and it takes a BIDS derivative too, because it takes a fMRI prep data set, which is actually a derivative data set, and it takes a BIDS statistical model. So I'm not going to talk in detail about what this is, but it's just a JSON representation of a design matrix, and to construct a design matrix and construct contrast. So this is an example of a way to, again, increase interoperability, is to create these standards that different tools can read and different tools can operate on. So this is what actually makes it possible to give Fitlins reproducible instructions to create results using a data set. So great, we have all these BIDS things though. So how do we actually deal with them? And so one tool that we've been working on a lot, and the primary developer is Talia Coney at this point. He's created a lot of, well, actually, she's just the main developer. PyBids is a tool for querying and extracting metadata from BIDS datasets. So this is a great tool if you're dealing with BIDS datasets to access them in a way that is programmatic. And essentially what it allows you to do is it allows you to make complex queries using those structured file attributes in a Pythonic way. So for example, in this example, I've built a BIDS layout, which is essentially just a representation of that data set. And it tells me your data set has 54 subjects and it has 1 run. And then I can tell that layout, hey, I want the bold file for subject 1, and I want you to give me back the file name. Okay, so I can do that. Once I get that, and actually I think there's a slight error here, but once I get that object back, because I can also get it back as an object, then I can ask, give me some of the metadata related to this file. So for example, what's the task associated with this file? What's the, oops, this typo is supposed to say repetition time. What's the repetition time associated with that volume? So this makes it really, really easy to parse and consume BIDS data sets using a pure Python API. So highly recommended if you're using BIDS data sets. And another aspect that's newer, and a little bit more alpha, if you will, is the bits model specification. So what we're doing here is using PyBits to take that specification and take that data set and essentially create a design matrix for us. So this makes it really easy to get a design matrix that's ready to run. But before we run anything, we need to read the data. And I mean really read the data. And so I think, sometimes something we take for granted are these really foundational pieces. And nibabel is one of those foundational pieces. So without nibabel, we really wouldn't be able to do any of this, because we'd have to go and look at nifty headers, and we'd have to read all these images and know all the different intricacies of how these work. So this is a really, really great example of a tool that makes the ecosystem possible, because we all use nibabel. We all expect nifty image, NiImage-like objects, so we can operate with those different types of objects. And so we don't have to worry about it. I will talk a little bit more about this later, but I don't have to care about how this is represented on the disk. I don't have to care about how this is represented on the memory. I can simply just use that object. And so this is great that we've sort of come to this standard, not just a library, but also object type. And then nilearn.stats. So this is a new module in nilearn that was previously niStats, that was previously NiPy, but it is a pure Python module for voxel-wise fMRI GLM. It has a consistent, easy to use Pythonic API, and it has support for all sorts of stuff that you might need to do such analysis, including hemodynamic models, design matrix creation, the statistical modeling, and of course reporting. And so this is honestly pretty much the code that Fitlins uses to actually do the model fitting. So as you can see, what I'm doing here, I'm basically just importing the first level model object. I'm importing the design matrix module and the plot design matrix module. And nilearn is taking that PyBids design matrix, and it's creating a design matrix. I think it's actually ending up in pretty much the same format, but it's adding a drift model. It's adding a couple things that you might want in your model that may not be there. And I think it's creating a dense representation of it. So now I can just take that and plot it. So that plot on the left was made in that next line, and then simply create a first level model object. And using a familiar fit transform API, I can give it the design matrix, give it the image, and get results. So yes, I noticed the docs were not merged yet, but the niStats still has some nice docs that you can go look at. But this is honestly, if you know how to use nilearn, you're going to know how to use this. Extremely easy, and it gets us away from FSL finally. So I mean, I actually think FSL is great in many ways, but what this is great is that when a bug comes up, which has happened, I've contributed to niStats, and it was great because it was really easy for me to go in there, find the bug, fix it, and contribute a PR. So highly recommended, and I think it's a great example. One thing I want to highlight here is that the way nilearn stats is designed, it was not designed with, I know there's really not that much hate for FSL, but the way nilearn stats was designed made it really easy for me to do this. And they didn't necessarily think of, any of what I'm doing as a use case, but because it's designed in a way that's modular, in a way that's, independent, it's really easy to use in a flexible workflow. So yeah, this is sort of what I said already. And so this is a great example. If you want to use it in a way that is more high level, there are some functions that make it easier. So for example, there's this function first level model from bids that will take a bids data set. You give it a task label, a space level, point it to a derivatives folder, and it will create your models. It'll give you the run images, the events, and the confounds. So you can fit this right into the first level model function and fit your model. So, different approaches. This doesn't use PyBits, but I think it's great because the way that, again, nilearn stats was designed, it did not assume that I was going to use this higher level function. So it gave me the option to use a lower level function that's more general while still providing a higher level helper function. So I think that's a great approach that I think nilearn embodies, and it makes for a really healthy ecosystem. So finally, pipelining. So We in Fitlins use NiPype, which arguably is overkill, but probably just because we're familiar with it. It works for us. It provides deployment via execution plugins. It provides disk caching in between nodes. But another thing you could do, which many of you are probably familiar with, is joblib. So joblib is used internally in nilearn, but it's just a lightweight pipelining tool for Python. It provides transparent and fast disk caching, easy native parallelization, and it's optimized for NumPy arrays. So again, an example of how in our community we have different approaches to the same solution. And if you, for example, were going to be dealing with other tools that are not in Python, you might want to use NiPype if you're familiar with it. I'm sure Chris can tell you more advantages. But if you wanted a lightweight approach, you could also use joblib. So we have those trade-offs there. So now that we've run our analysis, we want to share it. And so another way to do this is to have a standard output, and so I've already mentioned this a couple of times, but this BIDS derivatives is a standardized output for neuroimaging pipelines, and it captures the data and the metadata necessary for a researcher to understand and reuse these outputs in subsequent processing. So again, it's machine readable. And another thing I'd like to point out is that PyBids facilitates writing out these paths. So it's actually really easy to create a BIDS derivative data set using PyBids because you don't have to construct that path manually. You can just say, these are the attributes associated with this path that I'm about to create. Give me the file name. So I encourage you to read on this project if you're not familiar with it, because I think it's going to become something that we're going to see everywhere. And finally, visualization. So Fitlins generates comprehensive HTML reports of results. And again, that was really trivial to do because we have nilearn. So I was able to just take this plotting module from nilearn and give it a standard, nifty-like, NiImage-like object, and it's able to plot it. So again, a great example of a tool that was internally used in nilearn for everything, but is designed to not just be used internally. It can be used by other tools. So that was really the tour of the tools that Neuroscout relies on. And so I like to just close by, saying this sort of interoperability is really powerful. So by having tools that talk to each other and are designed in a modular way, it facilitates the creation of these high-level complex applications. You don't have to worry about how the layer works, And I think two main ways that we can do this are converging on standard data models. So for example, like I said, NiImage-like objects, nifty file formats. We can also converge on models for the BIDS data set, the BIDS stats model, the BIDS derivative. So these are, standards that we're all accepting and, allowing as input and output. But I think another important part, it's not just standards, it's also this modular design. So like I pointed out several times, a useful library will not necessarily make super strong assumptions as to how you're going to use your module. So it's going to be made as independent as possible from other modules in the library. So I can use the nilearn.plotting library, or I can use nilearn.stats, nilearn.stats. And I'm not necessarily an expert in other aspects of nilearn, but it was really, really easy to just take that aspect of nilearn and use it in my application. But modularity is really hard. I think there's actually a constant tension between, getting results now, getting those fast results that your PI wants, and, writing maintainable general purpose code. So I think, Gal talked on this earlier, but I think having that long-term vision really helps, realizing that this is not just because we like to design software. This is going to make better science. I think it's important to keep the basics simple in general. So, build small units that take general inputs, and then build high-level integration layers. So make your tool usable at different levels of abstraction. Don't just assume that everybody's going to come in and going to want to use your package in a monolithic way. Iterate and prototype. So, avoid premature over-engineering. That's easier said than done. Might take you a couple of years to learn that one. At least I'm still learning it. But I think it's something to keep in mind. And, be careful with releases. So if your software, if your package, if your library is maintained at a certain level of standard between releases, it makes it a lot easier to use in a more complex pipeline because I know what I'm going to get. And, one of the problems with modularity is keeping track of all the dependencies can be really difficult. And I think, there's also some social challenges. I don't know if this is a social challenge, but, hidden bugs can lurk in low-level packages. And working with these base building block packages, it's not as fun. It's not as exciting. For example, in nibabel, luckily we have some really dedicated maintainers like Chris, but it's not something that people necessarily want to touch. And I think people should try to, as much as they can, get involved in these packages. These are really important, and without them, we wouldn't be where we are today. So don't be afraid to look into the code for them. Don't be afraid to ask, is there a bug? I think sometimes it can also be friction between packages. So it's not necessarily always easy to adopt the standard. So I think that's just natural. I don't know if there's necessarily a solution, but it's just something to keep in mind. Harmonizing efforts can also be difficult. A lot of times someone creates a library, somebody else creates a library, does the same thing. And there's limited resources. Sometimes I ask myself, should these projects be joined? I think there's a lot of times that they should be, but I think there's also, that's just how science is. So people are going to want to try different things. I think that's perfectly okay. But I do think that this makes it hard for onboarding. So I think it's something to also keep in mind as developers, as people that are experts and familiar with all this ecosystem. I think, as beginners, I remember when I was first joining the community, it was just really overwhelming because, I would hear, oh, use DataLad, oh, use this, oh, use that. And so half of those packages, well, maybe not half of those packages, but a good amount of those packages that people told me to check out, they were just their pet project of the week. So I think this is something we need to be actively helping beginners with. So I think having courses such as this, there's so many courses now that really help this, but to give an overview of this ecosystem and to help onboard users so they can kind of pick out, these are packages that are actively maintained. These are packages that everybody's using. I think that's really going to help. But again, it's also okay, to build, I think, applications that are high level. Like Neuroscout is very high level. And I think, not all users will be developers, and that's also okay. We have to accept that. And I think one way to get people to come on board is to build these high level tools, and then maybe hopefully some of them will trickle down and use some of the more low level tools. And let's not forget, NiPype's a community. So again, let's contribute across the stack. Let's, keep making pull requests. Let's try to be, friendly and, responsive as much as we can in our projects. And just remember, we can talk to each other and figure these things out. And these better tools really are going to make better science. So hopefully the funding agencies continue to notice. So yeah, thanks to everybody. That's it. And if you have any questions, I'm looking at the chat. So happy to take any questions.
Okay, Alejandro, can you hear me again? Apparently he cannot.
Oh, and I can't hear you, but
okay, there we go.
I can see the text. Oh, there we go. I can hear now. I can hear.
Oh, okay, great. So first of all, thank you a lot for this amazing introduction overview into the Python ecosystem for neuroimaging. And before we forget, just that we have everything on board here, as I couldn't introduce you at the beginning, better late than never. Alejandro is currently working as a research scientist at the University of Texas, Austin. And you already got to know Neuroscout, so that's good. We actually have one question for you. Okay. And it's in the Ask a Question tab down there.
Oh, I see it. I see it now. I see older questions. So which one are you?
The third from the top. Otherwise, I can just...
The one about the... Yeah, just read it to me. I don't know which one you're talking about. Okay. Yeah. Resources on how to organize project, paper-specific repositories. Actually, I don't know if anyone else has a suggestion. I think Chris made a comment there. Yeah, I think NiFlows that Chris mentioned is a good one. But I think actually this might be something. I think it's something that we could work on, but I think it's also hard because I think projects can vary so much. It's hard to make, template that necessarily works for it. I'll see if I can think of something, but I think there's, like Elizabeth's saying, I think there's a lot of template makers that are not necessarily neuroscience specific. And a lot of times the way we organize our packages, I think just reflect how packages should be made in general, like Python packages. So I think there's some good suggestions there, but I don't know if it necessarily has to be neuroscience specific, except for maybe like papers. I think that might be something that it would be very useful to have.
Great, thanks a lot. We actually have 2 more questions if you go to the bottom of the question tab. See that one is
any conspicuously missing tool?
Oh, yeah.
I don't know. You tell me. Probably.
And the one above that, I think, is also for you.
Yeah, I think it is. This is the question is the distinction between modular and monolithic. I think it is fuzzy. I think it's fuzzy because a lot of the packages, like I was saying, FSL, and I only know I'm going to talk about FSL because I'm more familiar with it. But FSL is modular, so I think that's actually really great because we've been able to use it in NiPype in a modular way. So we can take a lot of aspects from FSL and combine them with other aspects. But I think what you're saying is that as a relative outsider, it can seem monolithic. And so I think it's really a distinction in terms of, like I was saying in nilearn, a lot of these little pieces can be used separately. So I think it's a fine distinction sometimes, but I wish I had a better example, but some of the code I wrote before, for example, I would write code for plotting, and it would require an object that was my object that was only I knew about in that library. So that plotting code would not work with just a general format. So I think these are the sort of things I'm talking about. And I think nilearn in particular, I can imagine why it seems monolithic because it has such a wide range of functionality. And so you can do, functional connectivity, you can do GLMs now, you can do machine learning. So I can see why, I can see why it feels that way. But I think when you actually try to combine these tools, the lower level modules, I think, are designed to be not monolithic, to be modular. So yeah, I think a lot of it just comes from, like I said, it's hard to get your head wrapped around how all the parts of the ecosystem talk. And I mean, to be honest with me, it took me like years to figure that out. So I think it's something we could work on. And I think education is what we need to do.
Thanks a lot for addressing all the questions. I think that's it actually for the questions and thus your presentation. Thank you so much again. It was amazing. Great to have you here.
Thanks. Yeah. All right. You go ahead and kick me off.